Good morning everyone. Welcome to Microwave Engineering video series. So in the previous two videos, we have seen E-plane T and H-plane T and its construction and S-matrix derivation, applications and different case studies and comparison between E-plane and H-plane we have seen in the previous videos. In today's video, we are going to discuss about what is magic T, what are the properties of magic T, the derivation part of S matrix for a magic T, and what are the applications of magic T that we are going to cover it in this video. So let's start our video. So magic T is also called as hybrid T, that is one name, or it is also called as EH plane T. The reason for calling hybrid T or EH plane T is the structure of the magic T is combination of both E plane T and H plane T. So in case of E plane T, so we have three ports. Port 1, port 2 are called as collinear arms, and port 3 we have named as a E arm in case of E plane T. Similarly, in case of H plane T, again it's a three port device. Port 1 and port 2 are collinear arms and port 3 is called as H arm. So if we combine both E plane T and H plane T, then we are going to have a magic T. So magic T is going to have total 4 ports. Port 1, port 2. So these two ports, port 1 and port 2 are called as collinear arms. And this one is E arm, that is port number 4 we have given as E arm, and this one is port number 3 named as H arm. So we have ports 1, port 2, port 3 and port 4. As we have seen in the properties of E plane T, if input is applied to E plane, E arm, if any input is applied to E arm, it is divided equally into output ports, that is port number 1 and 2 of same magnitude with opposite phase, and no output is obtained at port number 3. So here the important thing is, so right now we are discussing about magic T. In case of magic T, we are considering port number 4 as a E arm. So if you give input to this particular port, then we are going to have output at port number 1 and port number 2 with the same magnitude and opposite phase. And at the same time, across port number 3, there won't be any output obtained. That is very, very, very important. That is first important note. And second, if input is applied to port 3, that means we are applying input to port 3, that is H arm. That is our second note. Then the power is going to equally divide to port 1 and 2. Port 1 and 2 are going to have equal powers with the same phase like a H plane T, and no output obtained at port number 4. That means across E arm there won't be any output. So here in short, if I am giving input at port 4, this input we are going to get as a output across port number 1 and port number 2, and there won't be any output across port number 3. That is first one. So in this first case, the magnitudes across port 1 and 2 will be same, but phase will be out of or opposite phase. That is first one. And second thing is, if we are giving input at port 3, we are going to have outputs across port 1 and 2 with equal magnitudes and same phase. And across port number 4, there won't be any output. That is very, very important point. So, and third note is, in the previous two devices which we have discussed in the earlier videos, that is E plane T and H plane T, they are 3-port devices. So in case of 3-port devices, as we have seen in the S matrix of the previous derivations, it is not possible to make all 3 ports perfectly matched. That means in the case of E plane T, we have discussed only port number 3 is perfectly matched. and also the same thing for H plane T, that is S33 is equal to 0. But S11 and S22 are not equal to 0. That means they are not perfectly matched. That means in case of a 3-port devices, making all the ports perfectly matched is not possible. So in order to achieve this, so the solution is going for a 4-port device. That is nothing but the magic T. So one of the 4-port device is magic T that we are going to discuss in detail in this particular video. So overall magic T means we are going to have a 4 ports. So 4 port means the size of the matrix will be 4 by 4 square matrix. So we can write the scattering matrix for this particular magic T as matrix S is equal to S11, S12, S13, S14, S21, S22, S23, S24, S31, S32, S33, S34, S41, S42, S43, S44. So all diagonals, that is S11, S22, S33, S44, they are going to tell us the reflection coefficient value, which is similar to the previous two E plane and H plane discussion. So if you are assuming port 3 and port 4 are perfectly matched, then we are going to have S33 is equal to 0 and S44 is equal to 0. For a magic T, all 4 ports are perfectly matched. That means all diagonals should be equal to 0. But right now we are writing only S33 is equal to 0 and S44 is equal to 0. And we are going to prove the other S11 is equal to 0, S22 is equal to 0 in the next steps. Okay. Next, from the property of the E plane T, that is E plane T. So in case of E plane T, so we have S13 is equal to minus S23. S13 is equal to S23 for a 3-port device. In case of H plane T, we have S13 is equal to plus S23, right, with a positive sign. So if you consider the same concept for our magic T, so we are going to have S14. S14 means 1 will be your output and 4 will be your input port. That is very, very important notation. So always the first one is going to tell you the output and the second one is going to tell you the input. So if I am writing S14 means I am giving input at port 4 and observing output at port 1. That is S14. And S24 means giving input at the port 4 and obtaining output at port 2. So in case of E plane T, and also here we are talking about E arm, input is given to E arm. So we are going to have S14 is equal to minus S24 because they are out of phase to each other. So by using this particular thing, so we can write S14 is equal to minus S24 when you are applying input to the E plane T arm. Okay, that is port number 4. Okay, similarly, so if you give input to the port 3, that is H arm, then we can write as S13. Why S13? Because S13 means output at port 1 and input at port 3. So in that case, both port 1 and port 3 and both port 2 and port 3 are going to have in phase. So we can write S13 is equal to S23. That is S13 is equal to S23 because they are going to have the in phase. Whereas for the with respect to the port 4 and port 1 and 2, S14 is S14 is equal to S24 with minus sign. Okay, that is just now we have got S33 is equal to 0, S44 is equal to 0, S14 is equal to minus S24, S13 is equal to plus S23. So, and port 3 and port 4 are isolated ports. Isolated ports means in the note number 1 we have given if input is given to port 4, there won't be any output across port number 3. Similarly, if input is applied to port 3, there won't be any output obtained across port 4. That's why, so these two are called as isolated ports. So for the isolated ports representation, so we are writing S34 is equal to S43 is equal to 0. So S34 means what? At port 3 output and giving input at port 4, that is also 0, and giving input at port 3 and measuring output at port 4, that's also 0. So that's why S34 is equal to S43 is equal to 0. That is, if input given at port 4, then no output at port 3 and vice versa. That is one important observation. And next, by using symmetric property, that is Sij is equal to Sji. So we can write S21 as S12, S23 is equal to S32, S24 is equal to S42, S31 is equal to S13, S34 is equal to S43, S41 is equal to S14. So if you substitute all the conditions in our S matrix, then what are the conditions we have got from the previous steps? We got S33 is equal to S44 is equal to 0. And also we have got S14 is equal to minus S24, that is with respect to E arm. S13 is equal to S23, that is with respect to H arm. And S34 is equal to S43 is equal to 0, that is between isolated ports. That is a condition. So if you put all these conditions in our S matrix, original S matrix, so we will get changes here. So this will be, basically this is S23, but based on the symmetric property, this can be written as S32 or S23 we can keep, and we can utilize S23 is equal to S13. So we can get S13, and this one is minus S14, and this one is S13, again S13, 0, 0, S14, minus S14, 0, 0. Because S34 is equal to 0, S43 is equal to 0, and also S33 is equal to 0 and S44 is equal to 0. This is the modified S matrix based on the above conditions. So in order to further simplify the unknown values in the S matrix, unknown parameters in the S matrix, we can go with the property of unity property of an S matrix, that is S into complex conjugate of matrix S is equal to I, that is S11, S12, S13, S14, the same matrix, and its complex conjugate is equal to 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. It's a 4 by 4, right? So here, like in the previous cases, so we can have R1 C1, that is first row and first column, so we can equate. So what we are going to get, first row first column means S11 into S11 star plus S12 into S12 star, S13 into S13 star, S14 into S14 star. So already we have seen S11 into S1 star is nothing but modulus of S11 whole square. Similarly, S12 into S12 star, nothing but modulus of S12 whole square. Similarly, S13 into S13 star can be written as mod S13 whole square. Similarly, S14 into S14 star can be written as mod S14 whole square, which is equal to 1. In the similar way, if you go on writing second row, second column, third row, third column, and fourth row, fourth column, we are going to get 4 equations or expressions. So from the expression number 3 or equation number 3, so we can write 2 into S13 is equal to 2 into S13 whole square is equal to 1, or S13 is equal to 1 by root 2. Mod S13 is equal to 1 by root 2. That is from equation number 3. And similarly from equation number 4, we can write as 2 into mod S14 whole square is equal to 1, or S14 is equal to 1 by root 2. So we got 2 values. One is the value of S13 is 1 by root 2, and the value of S14 is equal to 1 by root 2. So now, so we need to further simplify the unknown parameters in the S matrix. We have got S13 value, we got S14 value. So we need to get what is the value of S11 and S22 and S12. So in order to get the other parameters, so we can simplify the equations 1 and 2. So if you if you compare equations 1 and 2, so we can equate these two equations, and this S13 from equation 2 and S12 from equation 1 will cancel. Similarly, S13 will cancel, S14 will cancel. Then we are going to have mod S11 whole square is equal to mod S22 whole square. Then we can get S11 is equal to S22 condition. That is the next for the same matrix. So if we write R4C1, row number 4 and first column, we are going to have S14 into S11 star, next minus S14 into S12 star, then 0 into S13 star plus 0 into S14, that is 0, is equivalent to 0. Then we can take S14 common, then we can write S14 into S11 star minus S12 star is equal to 0. And in the previous case, we have got already S14 is equal to 1 by root 2, which is a non-zero value. So the possibility of simplifying this is, we have to make S11 star minus S12 star is equal to 0, because it's a non-zero value. Already we have got 1 by root 2. So if we simplify this, we will get S11 is equal to S12 star, or S11 is equal to S12. This is very, very useful relation between S11 and S12. So if you put this particular S11 is equal to S12 expression in the first one, here S11 square plus S12 square, and already we have what is the value of S13, what is the value of S14. So here I can replace S12 with what? I can replace S12 with S11. So if you put it there, what you are going to get? So we are going to get S11 mod whole square plus, basically this is S12 mod whole square, but we can write S12 as what? S11. So here this is mod S11 whole square plus we have here mod S13 whole square. What is mod S13? Mod S13 is 1 by root 2 we have got. So 1 by root 2 whole square means 1 by 2. And next one is mod S14 whole square. What is S value? Mod S14 value 1 by root 2. So you will get 1 by 2 is equal to 1. So if you simplify this, so we are going to get S11 is equal to 0. So we can put all the values so in our S matrix. Then we are going to get S is equal to, matrix S is equal to 0, 0, 1 by root 2, 1 by root 2, 0, 0, 1 by root 2, minus 1 by root 2, 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2, 0, 0. So these 4 and these 4 will be same, and these 4 and these 4 you are going to get the same. So this is a final S matrix for the given magic T. So now we are going to go further and understanding the relationship between the input signal and the output signals. So that is nothing but output, that is matrix B is equal to S matrix into input matrix A. So this we are doing for your magic T. We can simply write the figure of the magic T as here port 1, port 2, and port 4 is your E arm and port 3 is your H arm. So we have written here B1, B2, B3, B4, and here our S matrix, here A1, A2, A3, A4. So in this case, we can write this B1 is equal to 0 into A1 plus 0 into A2 plus 1 by root 2 into A3 plus 1 by root 2 into A4. That is, we will get B1 is equal to A3 by root 2 plus A4 by root 2. Similarly, we can find B2 as 1 by root 2 into A3, that is A3 by root 2 minus A4 by root 2. Similarly, B3 is equal to A1 by root 2 plus A2 by root 2 plus 0 plus 0. That means A1 by root 2, A2 by root 2. That is B3. And B4 is 1 by root 2 into A1 minus 1 by root 2 into A2, then plus 0 and plus 0. You will get B4 is equal to A1 by root 2 minus A2 by root 2. So what we are going to do is we are going to understand different cases of inputs and the values of those inputs we are going to insert in these expressions, and we are going to understand what is the meaning of each case from these particular expressions. Okay, so let's assume, suppose let's take case number 1. So case number 1 is a4 is not equal to 0, comma, a1 is equal to a2 is equal to a3 is equal to 0. What does it mean? That means we are giving input at port number 4 and no input given at other ports. That means only giving at port number 4. Port number 4 means across E, across at the port 4, that is E arm, you are giving input and you are not giving any other inputs in our magic tree. So if you put this particular condition, that is a4 is not equal to 0 but a1, a2, a3 is equal to 0 in these 4 equations, what we are going to get? I am going to get b1 is equal to a3 is already 0. We are assuming a3 is equal to 0. So 0 plus a4 by root 2, that is a4 by root 2, and b2 is, if you put a3 is equal to 0, we are going to get minus a4 by root 2, and b3, b4 are basically in terms of a1, a2, so you are getting obviously b3 is equal to 0 and b4 is equal to 0. That means if I am giving input at port 4, if I am giving input at port 4, what you are getting? You are getting output at port 1 and output at port 2, that is b1 and b2, they are non-zero numbers, right? Getting output means non-zero numbers. Okay, so here b3 is equal to 0 means what? Across port 3 no output and b4 no output. That means what? Clearly it says that port 3 and port 4 are isolated ports. That means if you are giving input at E arm, that is port number 4, you are not going to get any output at port number 3, but you are going to get outputs in the collinear arm, that is port number 1 and port number 2. That is number 1 observation. The number 2, if you look at the values of b1, b2, they are having equal a4 by root 2, a4 by root 2, but there is a minus sign because you are giving input to the E arm, so you are going to get a out of phase outputs at port 1 and port 2. That is the meaning of a4 is not equal to 0 and rest all a1, a2, a3 is equal to 0. That is our case number 1. Similarly, let's assume if a3 is not equal to 0, comma, a1, a2, a4 is equal to 0. This is similar to the previous case. In this case, what we are doing? So we are going to give input at port number 3. A3 not equal to 0 means input applying at port 3 and rest all ports we are not giving any inputs. So in this case, what we are going to get? We are going to get b1 is equal to a3 by root 2, b2 is equal to a3 by root 2, b3 is equal to 0, b4 is equal to 0. So what does it mean? It means if you are giving input at port 3 means H arm. Okay, in case of our magic tree, port 3 means H arm. If you are giving input at port 3, you are going to get output across port 1, that is b1, and port 2, that is b2, and across port 3 there is no, because perfectly matched port, right? And b4 across fourth port 0, because across port 4 you are getting 0. So because port 3 and port 4 are isolated ports. So but the another observation is, if you look at the magnitudes, a3 by root 2, here a3 by 2, both are in the same phase, same magnitude and in phase. That is, if you are giving input at E arm, you are going to get output at first and second ports with equal magnitude and in phase. But if you are giving input at port number 4, and you are going to get outputs across 1 and 2 with equal magnitudes and out of phase. And one more thing is, in both the cases, if you are giving input across 4, there is no output across H arm, or if you are giving input at H arm, there won't be any output across E arm. That is case number 1 and case number 2. So let's find the other cases, that is case number 3. Let's assume a3 is equal to a4 is equal to a1 is equal to a2 is equal to 0. What does it mean? That means in the previous two cases, we have given only one input at a port, right? But now let's assume two inputs you have given, that is across port number 3 and across port number 4, you have given a signal A. And across 1 and 2, you are not giving any signal. Okay, in that case, we will see what we are going to get. So A3 is equal to A4 is equal to A. So if you put the these conditions, A3 is equal to A4 is equal to A and A1, A2 is equal to 0, then we are going to get B1 is equal to 2 into A by root 2, B2 is equal to 0, B3 is equal to 0, B4 is equal to 0. That means what? So if you are applying inputs at port 4 and port 3, then you are going to get output, at B1, that is 2 into A by root 2. 2 into A by root 2, that is the output we are going to get. And similarly, if you do A1 is equal to A2 is equal to A and A3 is equal to A4 is equal to 0. That means now if you give port 1 and port 2 inputs and port 3, port 4 no inputs, then we are going to get B3 is equal to 2 into A by root 2 and B4 is equal to 0. Similarly, case 5, if A1 is equal to A, that means only one port, first port, you are giving a signal and rest all ports you are giving a 0. So in that case, we are getting B1 is equal to 0, B2 is equal to 0, B3 is equal to A by root 2, B4 is equal to A by root 2. This is very, very important thing. That means, suppose this is my port 1, this is my port 2, this is my port 4, this is my port 3 of a magic tee. So according to this, what you are giving, I am giving input at port 1 and at all other ports there is no input given. So what we are getting, B1 is equal to 0. B1 is equal to 0 means the output at port 1 is 0 and B2 also 0 and B3 is equal to A by root 2 and B4 is equal to A by root 2. That means whatever the input you are giving, that is dividing across port 3 and port 4 equally. And at port 2, you are not getting any output. Similarly, if you give input at port 2 and if you are not giving any input at port 1, in that case also you are going to get output across port 3 and port 4 and there won't be any output across port 1. That means what? Which is similar to the isolation property of port 3 and 4. In case of isolation property of port 3 and 4, we have said that if any input is given to port 4, then no output will be absorbed across port 3 and vice versa, right? So in a similar fashion, if you are giving input to port 1, then you are going to get output across 3 and 4, but not across port number 2 and vice versa. Vice versa means if I am giving input across port 2, there won't be any output across port 1, but you are going to get output across port 3 and 4. So these are the possible cases of selecting different input signals and understanding the output from these expressions. So in the next class, we are going to discuss what are the applications of magic tee in the communication system, that is microwave communication. Thank you so much. Have a nice day.